Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Moortec with Stephen Crosher, who's going to talk today about thermal guard banding. Stephen, as we get down into advanced nodes, 16, 14, all the way down into what eventually will be 5 and 3 nanometers, power is obviously a big problem, and power dissipation is a problem, and that affects everything from consumer and data centers to automotive and IoT. How serious a problem is this? What do we do about it?
So thermal guard banding is a very important consideration for design teams. I have an example here that I just wanted to run through with you, which shows two different types of temperature sensor, both uncalibrated, one slightly more accurate, one slightly less accurate. So let's start with what this means for a less accurate temperature sensor. So we have a temperature scale of die temperature. We have a target temperature of 85 degrees C. So what does that mean for the software and the way you set the software to take action, whether that's to slow clock frequencies down in order to bring the temperature down of the device, or to maybe set a thermal or temperature alert within the software. So if you've got 85 degrees C as your target temperature, and your temperature sensor is, say, plus or minus 5 degrees C accurate, you then have a set point or a range of temperatures that can vary between 90 degrees C and 80 degrees C. So your software will need to be set at its lowest point, its worst case point, to 80 degrees C. So then, allowing for the inaccuracy of the temperature sensor again, so we're compounding this issue, you still have to allow for the plus or minus 5. So then the lowest point actually becomes 75 degrees C. Okay, so now if we take a more accurate temperature sensor, which is, say, plus or minus 2 degrees C, again, this is uncalibrated. You then have a temperature range of 87 degrees C and the lower part of the range being 83. So if you're setting your software to take action at that level, then you still have to take into account the inaccuracy, which is plus or minus 2, so that actually comes down to 81 degrees C. So this is the important point. We're now comparing the lowest set point for software at 81 degrees C with a good temperature sensor, and for a less accurate temperature sensor, it's 75. So just by using a slightly better temperature sensor, in this case, you could be saving yourself 6 degrees C of die temperature.
What does that really mean?
Well, depending on architecture and the application, 6 degrees C, better accuracy, could mean anything between, say, 5 watts and maybe 10 watts of power saving. As I say, it depends on the architecture. But what that means ultimately is that for power saving, for battery operated applications such as IoT and consumer, you can extend the battery lifetime. For, say, data center or telecoms applications, you can optimize speed and throughput of the device that much more. And for, say, automotive, it increases reliability of the devices, because you're then able to mitigate or help mitigate issues to do with stress and electromigration on the devices.